Hello, everyone, and thank you for coming to the SECAI workshop and to my presentation today. My name is Gibert, and I'm a Marie Curie researcher at CIDAR, which is Ireland's Centre for Artificial Intelligence. And I'm currently working on a research project with IBM Research Ireland to investigate how machine learning malware detectors can be improved to be more robust against adversarial attacks. So today I will present our work titled Towards a Practical Defense Against Adversarial Attacks on Deep Learning-Based Malware Detectors via Randomized Smoothing, where we will explore how randomized smoothing, which is a technique, a defense employed to defend image classifier against LP attacks, can be adapted to increase the robustness of deep learning-based malware detectors. So this research paper is a joint work with Dr. Quan from CIDAR and Dr. Giulio Zizzo from IBM Research Europe. This is the outline of the presentation. First of all, I will briefly summarize the main types of adversarial attacks specifically developed against machine learning based and deep learning based malware detectors. And afterwards, I'll present a randomized smoothing based approach to improve the robustness of the detectors. And later on, I will provide an empirical comparison between the smoothing based detector and a baseline malware detector, where we will see that in general, our approach achieves higher detection accuracy on the adversarial malware examples. And finally, I will conclude by outlining the limitations of the proposed approach and defining some future research directions. So malware detection refers to the task of determining whether a given piece of software is benign or malicious. To sum up, static machine learning-based malware detectors can be divided into two main groups. On the one hand, feature-based detectors rely on feature engineering to manually extract a set of discriminate features from files. And on the other hand, deep learning-based detectors omit the feature engineering process by directly learning patterns from raw bytes. And these end-to-end detectors, take as input raw bytes representing the computer programs and output a label indicating whether the file has been classified as benign or malicious. In the context of malware detection, given a malware detector, the goal of an adversarial attack on a malware example is to produce an adversarial malware example that has the same functionality as the original one, but the malware detector or the target detection system classifies the adversarial malware example as benign. And in this work, we'll focus on deep learning-based malware detectors, as they have been shown to be very susceptible to adversarial attacks that manipulate the content of a program. Broadly speaking, evasion attacks against deep learning-based malware detectors can be classified into three groups. Append-based attacks are the attacker appends new content at the end of the file, which is known as overlay append. And patch-based attacks, the attacker patches or modifies existing content within the file. For instance, you could manipulate the bytes located in the code gaps between sections. And lastly, injection-based attacks, the attacker injects new content within the file, and this can be done, for instance, by creating new sections containing the adversarial payload. So far, the only defense that has been published to defend against adversarial malware examples is adversarial training. Adversarial training works by augmenting the training data by transforming the clean examples with the adversarial attacks used to evade detection. As a result, the adversarial training model will be more robust against the known adversarial attacks used to augment the training data, but also it will be more sensitive to subtle changes in the data, which might lead to a reduction in the accuracy against clean real-world data. In addition, adversarial training has limited effectivity against adversarial attacks not seen during training. So the more different are the adversarial attacks from those seen during training, the worse is the accuracy of the model. And furthermore, generating adversarial malware examples is computationally expensive and non-trivial, and as a result, training models with adversarial training typically requires more computational resources compared to standard training procedures. For instance, Kim Lucas investigated the effectiveness of using adversarial training to build end-to-end classifiers that are more robust to some state-of-the-art attacks. So they conclude that that augmentation does not deter state-of-the-art attacks, but in some cases, models can be made more robust to malware domain attacks by adversarial training them with lower effort versions of the same attack. For instance, they augmented the training data with adversarial examples generated by three attacks: the in-place replacement attack, which replaces equivalent sets of instructions; the displacement attack, which displaces code and uses jump instructions to pass the control to the displaced code; and the padding attack, which pads bytes at the end of the executable. And afterwards, they evaluated the training model, the adversarial training model, against an attack that combines in-place replacement and the displacement attacks, and found that the adversarial training model's accuracy to the combination attack is on average 49%, whereas the original model accuracy without adversarial training is 23%. So instead, in our work, we have explored how randomized smoothing can improve the robustness of end-to-end malware classifiers. In contrast to adversarial training, smoothing-based classifiers aim to smooth out the decision boundaries in the input space, making the classifiers more robust against a wider range of attacks. Randomized smoothing is a method used in machine learning that averages a model's output in relation to randomized inputs, and this method has recently gained attention in the computer vision domain because of its capacity to reduce a model's sensitivity to noise or fine scale variation. And more specifically, it has been shown that randomized smoothing schemes employing Gaussian or Alpine noise when randomizing inputs provide LP robustness certificates. And these randomization techniques, however, are inadequate for the task of malware detection because they erroneously assume numerical input values and they erroneously assume all input examples are of the same size. However, byte values are categorical and are often embedded as a vector of real values, and the size of the input files vary. To address these limitations or these incompatibilities, we proposed a randomized aberration-based smoothing scheme which randomizes the input examples by randomly ablating a percentage of the bytes in a given binary file. In a randomized aberration-based smoothing scheme, a base classifier is trained to make classifications based on an ablated version of a given executable file. And this ablated version consists of a copy of the original executable file with all the selected byte values replaced or ablated with the specially encoded path symbol. And this path symbol is encoded as a vector of zeros, and the rationale behind is to conceal the information of the selected bytes from the classifier. And during testing, we generate L ablated versions of the original file and classify each ablated version separately. And afterwards, to calculate the final score, we count the number of ablated versions that the base classifier returns for each class, and we divide it by the total number of ablated versions. If the score is equal or higher than 0.5, then the example is classified as malicious, and otherwise is classified as benign. In this paper, we have used the BODMAS dataset to evaluate the proposed randomized aberration-based classification scheme, and this dataset consists of 57,000 malware examples from 581 families, and also 77,000 benign Windows portable executable files that have been collected from August 2019 to September 2020. And the BODMAS dataset has been partitioned into three sets: training, validation, and test sets, taking into account the timestamp of each example. So the examples in the training set contain the older executables, while the examples in the test set contain the more recent executables. And to speed up the experiments, we have only considered those executables that are equal or smaller than 1 MB. And the rationale behind is that the greater the input size, the greater the computational time required to run the experiments. And furthermore, as some of the Bayesian attacks evaluated manipulate executables by injecting content, the bigger executables will have to be clipped to fit the model. By using executables that are equal or smaller than 1 MB, we avoid having to clip the executables and, in consequence, losing important information for classification. So the total size of the reduced dataset consists of 39,000 and 37,000 benign and malicious executables, respectively. So in this work, we experimented with a deep learning-based malware detector named Malcolm. Malcolm is one of the first end-to-end deep learning-based models proposed for the task of malware detection. So end-to-end models learn to classify examples directly from raw byte sequences instead of relying on manual feature engineering. And the network architecture of Malcolm consists of an embedding layer, a gated convolutional layer, a global max pooling layer, and a fully connected layer, as you can observe in figure 4. Using Malcolm as a basis, then we train two malware detectors. NS Malcolm, this is a detector that corresponds to the non-smoothed Malcolm model, and it serves as a non-robust baseline, as no specific technique has been employed to improve the robustness against evasion attacks. And then we have RA Malcolm, which is the detector that implements the randomized aberration-based smoothing scheme using Malcolm as the chunk classifier. The randomized based aberration scheme is controlled mainly by two parameters, which are the proportion of bytes to ablate with respect to the file size and the number of updated versions of a given file that are used for classification, which is denoted by L. So these two parameters affect the way the method operates and the output it produces. On the one hand, the greater the number of updated versions, the more stable is the output of the classifier, but also the more computational time is required to classify an input example. On the other hand, the greater the number of bytes ablated or the proportion of bytes ablated, the lower the classification accuracy of the smooth classifier. In our experiments, the best results were obtaining by ablating 20% of the bytes in a file and by generating 100 ablated versions per input example. In table 1, you can observe the accuracy in the F1 score of the non-smooth and the smooth Malcolm models on the validation and test data. And you can observe that the accuracy is very similar between both models on the clean data. Since some attacks might take hours to run per file, we also have used two smaller sized test sets containing 500 and 100 malware examples randomly subsampled from the test set. So the test subset consisting of 500 examples have been employed to evaluate the malware detectors against the padding attack, the shift attack, and the gamma attack. On the other hand, the test set of 100 examples has been used to validate our models against the code caves optimization attack. So by employing a smaller dataset, we aim to reduce the computational overhead and accelerate the overall experimentation process. In addition to further accelerate the experimentation process, we also have reduced from 100 to 20 the number of updated versions generated for each input adversarial example. In our work, we have considered 4 recently published evasion attacks designed specifically to bypass static deep learning-based malware detectors. So these attacks manipulate the executables by appending new content at the overlay, creating new spaces within the executable, and by injecting new content in newly created sections. For instance, the slug plus padding attack injects an adversarial payload at the end of the file in its overlay, and then it optimizes the content injected and the bytes in the slug space of the executables using the fast sign gradient method. The shift attack works by creating some space between the headers and the sections of portable executable files, and later that content is optimized with a single gradient step. On the other hand, the gamma attack injects the adversarial payload into newly created sections, and then the content is optimized with a genetic algorithm. And lastly, the code caves optimization attack extends the space between sections and optimizes the content in these code caves with a genetic algorithm. I would like to point out that the white box attacks cannot be directly applied to a randomized ablation-based classifiers as they require computing the gradients, and our approach makes computing the gradients a difficult task because of the Armax function used to calculate the final classification score. To circumvent this limitation, we optimize the adversarial payload of these white box attacks using genetic algorithms. So the use of genetic algorithms to optimize the adversarial payload allows us to convert the white box attack to black box attack, and therefore there is no need to access the implementation details of the model or the gradient information to optimize the payload. Instead, the genetic algorithm will explore the search space by imitating the process of evolution through various P-inspired operations like selection, crossover, and mutation to optimize an initial population of solutions. Similarly to gamma, the initial population of solution is initialized with benign content, and in our experiments, the size of the population is set to 50, and afterward, the genetic algorithm applies selection, crossover, and mutation to optimize the injected adversarial payload. So table 3 present the detection accuracy of the non-smoothing based Malcolm and the randomized smoothing Malcolm models on the adversarial malware examples generated by the aforementioned evasion attacks based on genetic algorithms. And table 3 shows that regardless of the evasion attack, the randomized smoothing Malcolm outperforms the non-smoothing Malcolm by some margin. For instance, the non-smoothing Malcolm detects 43 and 40% of the adversarial malware example generated by the shift attack, while the randomized smoothing Malcolm detects 69 and 67% of those adversarial examples. Also, the randomized smoothing Malcolm provides greater detection accuracy than the baseline on the adversarial malware examples generated by the gamma attack, showing that the proposed defense mechanism holds its ground against evasion attacks that inject and optimize huge or great amounts of benign content. And lastly, the randomized smoothing Malcolm detects 81% of the adversarial malware examples compared to only 40% detection rate of the the non-smoothed Malcolm, when the adversarial examples have been generated by extending and optimizing the code caves in the executables. And overall, the robustness of the randomized smoothing Malcolm to attacks that manipulate the executable is positive and a great improvement over the baseline, demonstrating that anti-malware engines can benefit from smoothing-based schemes. However, the increased robustness against adversarial attacks comes at the expense of increasing computational time, as you can observe in Table 4. And this is because the non-smoothing detector only has to assess once the maliciousness of a given input example. On the contrary, the smoothed detector is slower because it needs to assess each ablated version of the input example independently and then aggregate all the predictions. Nevertheless, the benefits of the increased generation abilities and robustness to adversarial attacks provided by the smooth detectors outweighed the added computational cost and time required for classification. Also, we would like to point out that the test time could be decreased by using parallelization and also by optimizing the code. Lastly, our results suggest a number of directions for future work. The most apparent direction identified is the incorporation of recent defenses from the computer vision domain other than randomized smoothing. To this end, we have explored how a deterministic approach, how the randomized smoothing can be adapted into static malware detection models to prevent a localized injection of benign content or to prevent small payloads from containing adversarial content from dominating the prediction. And another line of research could be investigating approaches to identify and remove the adversarial content from the executables. And this is everything. Thank you very much for your attention.
For clarification, so for your evaluation, did you maybe look at or did you compare with static and dynamic detection? Because some detectors will work on static features, but
No, no.
also look at behavior, and is there a difference in your approach?
It's only whoa. It's only a static analysis. So we are only looking at the bytes of the executables. We are not running those executables on a virtual environment.
What would the impact be if you would compare it dynamic behavior? Do you think there might be further room for improvement, or?
I mean, with dynamic analysis, you can extract different type of information. So right now, here we only have the bytes, right? But with dynamic analysis, you can get the instructions that is being executed on the machine. You can get the articles and so on. So it's different information that you can extract. So probably it's going to have different results too. I don't know with that.
Yeah, and the adversarial samples that you generate, do they still compile and run?
Yeah. Yeah, I use it leave, which is a library, a Python library to manipulate portable executable files.
Any other questions? In the area of malware detection, the adversarial attacks techniques and randomization techniques which you presented are novel, or there are like other techniques also, and we ask maybe from other subdomains of adversarial attacks, not cybersecurity, but maybe attacks on images or other data. Maybe there are some methods you would think of using in your case.
To define malware detectors.
Yeah.
Yeah, so there is like this kind of approach that's named the randomized smoothing, which is the one that we are going to be presenting at ISEC. So we basically, in this case, in this approach, randomized smoothing, we just replace some of the bytes with some probability. So with the approach we're going to present, we are just extracting chunks from the executable and classifying those chunks independently. And by doing so, we are able to provide some robustness certificate against attacks. So we can be able to say, okay, so you have this malicious executable. We can assure that it's not going to be detected as benign as long as you don't inject such amount of bytes.
So I have one question. So what kind of model did you use in your evaluation? I mean, there are several approaches for code analysis, natural language processing, or translation from code to images. So what kind of approach did you use for evaluation?
In the architecture of the network, how we process the data, or
I mean, how to use code. Yeah. So on this point, so you give a low byte
Yeah.
to machine learning model.
Yeah.
As before, so what kind of so
So-
approach did you use? So from translation from low byte to some kind of natural language processing, or
yeah,
photo to image?
we convert each byte to a word embedding. So the first layer, the embedding layer, converts each byte to a word embedding, like a vector of real values,
I see.
like similar to text classification.
Yeah, I mean, my another question is, so can we use this kind of approach to natural language processing? I mean, so another technique of code analysis is to utilize natural language processing for low byte or byte code. So I'm not sure whether randomized smoothing is also available for natural language processing or not.
I'm not aware of that. I don't know. I didn't check it. It has been used for defending. You mean to defend, like you have a text classifier and you have an attack that I want to manipulate the, I don't know, the label of the text that has been assigned. I don't know if it has been done that.
Okay. Okay. So let's start again.